Recording. All right, you guys hear me on the Discord?
Yeah, you're good.
Do you have me like in here?
Yeah.
It's not gonna get weird. It's not like, is there like, surely there's some latency.
Yeah, it's like, it takes a moment for me to
Yeah.
process it.
Okay. All right. Are there, good afternoon, guys.
Good afternoon. Good afternoon. Good afternoon. Good afternoon.
You didn't say it. Good afternoon.
Good afternoon.
All right. Are there any questions, comments, concerns?
I had just a quick question
What's that?
regarding the Python project.
Yeah.
So with what you showed us in class, I couldn't figure out a way to play any notes shorter than 1 second. Like I can play my songs, just play them really slowly. Like if you want to play an 8th note or a 16th note, it needs to be longer, or it needs to be shorter than a second.
So like the player won't play anything?
I mean, because it won't, like, I think for the lin space function,
Yeah.
it won't take in a float. It like messes everything up.
Okay, yeah, so I forget the name of the student, but I had a student in office hours the other day, maybe it was Monday, talking about this exact thing. In fact, let me just sort of jot down a little bit. Remember that when you're creating the lin space, I'll erase this in a second. When you're creating the lin space for your song, that's the in, right? That's the in our X of in. Can that be a float?
No.
No, what does it have to be?
Integer.
It has to be an integer, right? So that has to be an integer. That was tripping some folks up.
I think I just typecasted it.
Well, that's a dangerous game to do too, right? Because then you're gonna have stuff kind of get stuff's gonna cut off, right? If you're like doing like a floating point range, and then you typecast it to integers, then you're gonna get like weird stuff. You're even gonna have values with the same like ins that are the same value next to each other, right? Because it's going around. So don't do that. That's going to create all kinds of problems. If you're done and it didn't cause all kinds of problems, then I think you just got lucky.
Yeah, I guess so.
But the way you're supposed to do is you got to start with an integer. So since Hunter already admitted that it was him in office hours, yeah, Hunter. So this is the same thing. But you don't want to force it to be an int because that can lead you to bad places. You never want the compiler or the interpreter, I guess, in Python to like make decisions for you, right? And if you typecast to an int, you just open yourself up for problems. I guess if it worked out, it worked out, and you probably got sort of lucky, but probably because at the end of the day, it didn't really make a difference. But I would be interested. I think it's worth go actually look at your linspace array and actually see if you've got like duplicate things or places where stuff got messed up. What you really ought to do is just start with integers, right? So 0, 1, 2, 3, 4, 5, all the way out. And then use your sampling rate to sort of affect like the timing of things, right? So you might say like, what's the, the fast, in the song that I picked, like what is the shortest note, like a 16th note, maybe it might be the shortest, and say, well, that's gonna be, 4 samples or 1 sample or something like that. Probably gonna do more than 1 sample because 1 sample is not very interesting. But you gotta sort of pick a length that is going to be appropriate for your smallest one and then expand it out from there. So, and you don't want to play the individual notes. So you don't want to play, I guess you could get away with this. But since you've got to convert it to a .wav file anyway, what you want to do is you want to make it one long array that is your whole song.
Yeah, I didn't do a .wav. I have an array for my notes, and I have an array for the seconds, how long you play each note. And then I pass that into the lin space and
it does the stuff, yeah. But I'm saying at the end of the day, though, you're gonna have to have an array that's your whole song. Mm-hmm. Yeah, because that's what you're gonna want to play instead of like hitting the play function over and over again on different notes. Is that what you're doing? Is that what you're saying?
I just have an array. I just have an array of notes, an array of how long each note is, and then I pass it in and run all the stuff with the lin space and the sample rate and stuff, and then I create the play object and then I play it.
Gotcha. So how are you going to convert that to a .wav file?
We have to do that for the project. I don't see that in the description.
I don't think it said.
Did I not say it in the description?
I don't think so.
I meant to say it in the description.
I think you might have said it like out loud.
Hold on. Let's go to the thing. I'm going to look this up right now. Dang, I'm going to be really mad if I didn't put it in the description because I wanted you to do that because I wanted to force you to like synthesize one array that was the thing. No, you're right. All I said was you got to play it. Dang. Bank error in your favor. All right, cool.
So in the documentation for the
Dang, I really wanted you to do that. You should still try to do it. It's a good exercise.
the module that you gave us, it gives us like a how-to on how to add all that stuff to an audio array.
Mm-hmm.
Could you have also done it like your way with using threading?
My way using thread. What do you mean by using threading?
Like making it a multi-threaded application?
Like play.
Like playing...
Like play both voices on different threads?
Yeah. Is that another way you could have done it?
I don't know. I'm not sure you can play.
I was just curious about it.
I don't think the audio driver can live on different threads. You know what I mean?
Yeah.
Like, I'm sure you could, like...
That's why...
I'm sure you could do the process in different threads. But if, at the end of the day, it played on audio, I think it still has to be... I don't know if you can multi-thread audio output. Maybe you can, though. Maybe that's why...
That's why I didn't do it, because I wasn't too sure if you could.
Again, I mean, the point of the class is to, like, you know, learn and explore. You should still try it in the same way that he should still try to make a WAV file from his thing. You should try it. Like, try multi-threading the audio and see what happens, right? That'd be pretty cool. So, if you've got time, of course.
Yeah.
And you got other stuff going on. But that would be an interesting thing to see. Maybe you could, because I know you can have multiple audio channels, right? I could be playing audio out, like I could play music on Spotify and be like chatting here in the same time. So clearly there exists some multi channel audio thing.
Yeah.
I don't know. If you got time, check it out. It'd be pretty cool. Yes, hold on. So let's see. Brene asks, for the two voices, did that mean we just need two tones to play at the same time? Yes, basically that just means you have to have two different tones, two different signals at the same time. You got to create a harmony. If you wanted to be a little bit more creative with it, you would make one tone distinctive from the other. So make like one voice a sine wave playing the notes, and the other one be like a sawtooth wave that's playing the notes, or a square wave that's playing the notes. So that way you get some like weird sort of musical play. But again, that's just sort of up to you if you've got the time to be creative and have some fun with it. If not, yeah, two sine waves will check that box. And yes, I know I had said on lecture on Friday that I was thinking about the two voices to be extra credit. I ended up making that mandatory just because I think that would be pretty cool. Also, it's really easy. You literally just add them together on top of each other. So, all right. Any other questions about the Python project? Yes. Cole says make sure you renormalize after you've added. You're absolutely correct. Otherwise, weird stuff happens. All right. Any other questions? All right, let's have our class today. So let's see, we are done with chapter 1, and today we're starting, or excuse me, we finished chapter 2. It always tricks me that the book actually starts on chapter 2, where we did a bunch of weird stuff, and then now we're in chapter 3. We're going to start talking about the Z-transform in a real way, which is to say, like, can we get to a place where we can actually start doing interesting things with the Z-transform. So let's say, let's get some definitions going. So I'm going to say this. In chapter 2, we defined the discrete Fourier transform. We defined as this. Remember, we got big X, capital X of e to the j omega is equal to the sum, or the sequence, in from negative infinity to positive infinity of x of n times e to the minus j omega n. Now, we already talked about this, actually sort of in a tangential conversation that we had in class, but to get the Z-transform, we simply substitute do the substitution, we're going to say that z is just equal to e to the j omega. And we already knew that. Which gives us the Z transform. And we say big X of Z is equal to n negative infinity to positive infinity x of n times z to the negative n. All right. We already kind of knew this was the case, but we have to restate it. Occasionally, we're going to use the Z transform operator just to simplify our notation a little bit. So I'll say this: occasionally, operator was just this, kind of like everything else. Fancy Z in brackets of x of n is equal to our Z transform. Big X of Z. One last notational thing is x of z, not x of s, that's the Laplace transform, x of z. And by x of z here, I mean the one where we use n equals negative infinity to plus infinity is called the two-sided or bilateral Z transform. And so if there's a two-sided or bilateral Z transform, we also define a one-sided or unilateral Z transform.
So in the Z transform, we're always in the same frequency?
What's that?
We're always in a singular frequency when we're doing the Z transform?
I mean, that depends largely on what you mean by singular frequency. However, the Z transform does not, in the same way that the Fourier transform does not change the frequency, the Z transform doesn't change the frequency either. It just converts us to frequency domain. And again, like we talked about before, let me finish writing this, unilateral. The Z transform is the Fourier transform. We're just using Z instead of e to the minus j omega, or e to the j omega.
And then n would be the phase, right?
Yes, yeah. But you're getting ahead of me again, man. So we're going to do like a chi or a fancy Z of x is equal to a one-sided. It just basically means n equals 0 to infinity x of n z to the minus n, right? So pretty simple. That just means that if we say a bilateral or two-sided, that means Z transform from negative infinity to positive infinity. If we say one-sided or unilateral Z transform, we mean from 0 to infinity, right? Which makes sense. You'll see the bilateral is a pretty commonly used in mathematics, right? It's a little bit more theoretical. In practice, the one-sided that starts at, n equals 0 is a little bit more used in application.
By the way, Professor, are you recording?
I am recording.
Okay.
Let's double check though, just to make sure. Yeah, we are. Okay. So our claim that the Fourier transform is the same as the Z transform is mostly true, but isn't quite exactly true. what is true is that that the Fourier transform that we spell correctly is a special case of the Z-transform. All right, because we've been lied to just a little bit. The Z-transform isn't Z equals e to the j omega, it's actually Z equals R times e to the j omega. So this is the real substitution. All right, so what that means is, relax, come back. X of z is equal to, we'll stick with the bilateral for now, of x of n, well, it's still gonna be the same stuff, z to the minus n, which if we break that open and take a look at it, it's going to be x of n times r to the negative n times e to the minus j omega n. So we have this extra r to the negative n kind of hanging out and messing stuff up. So with that being said, who can tell me what is the special case of the Z-transform that gets us the Fourier transform?
R equals 0?
Not 0.
1? Or
1.
1.
Yeah, right. 1, 1. So that's the thing. When R equals 1, then fancy Z is equal to fancy F, right? When R equals 1, the Z transform is equal to the Fourier transform. They're the same thing. But that makes it interesting to look at, well, what happens when R is not equal to 1. So let's dig into that. The next thing we want to do is we want to start plotting the Z-transform. We're going to use these plots as tools to design our systems. So plotting the Z-transform. Let's start with this, that Z is equal to R times E to the j omega means that it's complex. Z is a complex number, which means we have a real component, or the magnitude, or the real bit. Then we have the imaginary bit, which also gives us the phase of our sinusoids if we're doing it that way. So we have a real component, we have an imaginary component. So we're going to plot the Z-transform in polar coordinates. Polar coordinates. And that's going to look like this. So we have a horizontal and a vertical axis. On the horizontal axis, we'll do the real part. On the vertical axis, we'll do the the imaginary part. And then just the normal, let me put it in blue here, z is equal to 1 times e to the j omega. It's just going to take the form of a circle. Just like that. So the distance from the origin, different color.
Is there any reason why we would want R to not equal 1?
Yeah, there's lots of reasons why we want R to not equal 1. In fact, we're going to talk about it starting today. So that's going to be R, whatever that angle is omega. Right? Everyone remembers polar coordinates from like pre-cal, right? Okay, so that's just if R is equal to 1, right? We get this guy, we call it the unit circle. All right. Unit for 1, circle's at 1, unit circle, life is good. But here's the deal, R can be not equal to 1. And in fact, let's go back and look at this. In fact, I'm going to write that one more time. So if I say that x of, just to make it easier, r e to the j omega is equal to the sequence. If you don't mind if I get lazy and stop writing in negative infinity, positive infinity? And if I just write sigma, that's what it means? Okay, no one's going to get freaked out by that? All right. I'm just tired of writing it all the time. So x of n, I have r to the negative n, e to the minus j, omega n. Now, in what math class did you guys talk about sequences and series? I know I was getting in trouble when I asked for your prerequisite knowledge. Cal 2, right? And what was the important thing? Like, you spent time, you remember that?
I think so.
It happens at the end. It's like the last thing you talk about in Cal 2.
Oh, okay.
And it's after.
The Taylor.
Yeah, Taylor McLaurin. You did tests, like the ratio test and the root test and all those like fun ones and stuff like that to find out if a sequence or a series converges. Yeah, go dust those notes off. So what was the important thing there? Yeah, those. I don't know. I thought they were kind of fun. Is whether or not the sequence or the series converges, right? Because that tells you a thing. And for us, we care about whether or not this series converges. Why do we care about that? What do we think?
That it'll be a stable system.
You see, the problem is you read the textbook and you know the answer to all my rhetorical questions. You just have to stop answering, or you're taking all the fun out of it. Yes, as Edward said, Mr. Know-it-all. You care about whether or not the sequence converges because, for us, convergence equals stability. Like that. I want to draw a box, right? Because it's important. Seriously, I want to draw a box. Oh, there you go. Now you give me the box. Sometimes one note is the worst. Cool. Okay. Convergence equals stability, right? When we design our system, whether it's specifically stability is really important for things like controls. So if you're designing a drone that flies, right? You got to have those control systems, those feedback. That's still a discrete time signal processing problem, right? We have to filter the signal and apply the control signals and stuff like that. If it's not stable, it means your thing is going to crash, right? For audio signals, that means whoever is, heard anyone on a microphone and that crazy high pitch, feedback thing happens. Well, what is that?
Like that noise that goes like.
Yeah, right. You guys talking to the microphone and you start hearing that like that whine, that feedback?
Yeah.
It means instability, right? It means in that audio system found it, the little Z-transform, this plot, this circle went to a weird place, got unstable, and you know, it wanted to sort of diverge to infinity, and you got feedback, and your friend's wedding was messed up, you know, or whatever. You know how they fix that? In situ, in real time? What's that?
A limiter?
A limiter. A what?
Like an audio compressor, like if something is above a certain decibel range, to cut it or something?
No, so what they do is, I've seen it happen like in real time, like the sound, the AV guy will be standing there with a device that basically just takes the Fourier transform of the feedback, right? So if you measure the frequency of that feedback, right, that'll tell you the place in the signal where it's diverging, right? And then you go to the equalizer on your soundboard and you turn down that frequency, and that stops the feedback. So, yeah. So for us, we care about whether or not our Z-transforms converge, because that will directly correlate to whether or not our systems are stable or not. So we want systems that converge because we want systems that are stable. Did I say that enough times? All right. So, and convergence, or not, will depend largely on the value of R. All right. So instead of plotting a circle, we'll plot what they call the region of convergence. Or the rock. Which leads to fun phrases like plot the rock or make the rock plot.
The Dwayne plot.
Well, that's what we're going to call it from now on. All right. So we're going to plot the region of convergence. And the rock plot can take on three forms, basically. The first one is simply the disk. So, why can't I do that correctly? The real, the imaginary will plot. One note. All right. That's going to be at whatever R is. We fill it in. Get to bust out your coloring skills. So, what that means is that x of z converges for the magnitude, the real component of z is less than or equal to r. Right? So inside the region, our system will converge. Cool? That's the disk. Form number 2, this is going to get pretty obvious, is the ring. There's no shocker there. That means that inside this region, our Z converges, right? So if we say that this is like RA and RB, magnitude of RA is less than or equal to magnitude of Z is less than or equal to the magnitude of RB. There's some window, some narrow region in which our system will converge. And then finally, bull. Right, no shocker here. This means that everything outside the ring converges. Right, so if that's R, we say that the magnitude of Z now must be greater than or equal to magnitude of R. So those are the 3 basic forms, right? And it sort of covers all the bases, right? Either Z converges going outside to forever, fits inside some narrow range, or goes from R in, right? It's going to be one of these 3 options. Let's see. And mathematically, how do we figure out, how we figure out what that is we say that the rock is the region for which the absolute value, the real component of our Z-transform, is less than or equal to that. I'll go ahead and write it this time. Plus infinity, the absolute value of x of n times r, the negative n, is less than infinity, right? It's the place where this thing is what's called absolutely summable. It has some closed form solution. It has some value. It doesn't just go to infinity. It has to stop somewhere. All right. And then the last thing, before we work out a couple of examples and get out of here, is that, so this will be true, or when this is true, come on. We can represent our Z-transform as this. We can say that we have, actually I'm not done writing. We can represent x of z as a closed form solution, which is to say that x of z is equal to this, or we call p of z over q of z. Where p of z and q of z are both polynomials of z. Okay. Now let's do a couple of examples. The problem is loosely stated as this. Plot the region of convergence. Plot the rock for this sequence. X of n is equal to a of n times u of n. Right, the unit step function, step sequence, excuse me, times a to the n. So step one is always going to be, find the Z-transform of X of n. So let's see, big X of Z is going to equal the sequence x of n, which is a of n, times u of n times z to the negative n. No problem there, right? Just substituting stuff in. Okay, now we can sort of notice some things. What happens with u of n? Exactly, right? It's going to take our bilateral sequence and convert it to a unilateral sequence, right on. And then we get rid of u of n because it's done. All right, so that's all u of n serves to do, is convert our bilateral into a more realistic unilateral, z to infinity, I have a of n times z to the negative n. Okay. So now what we want to do is we got to figure out where this thing converges, right? And we're going to do that by combining a of n and z to the negative n. So make a note of the fact, so let's note that z to the negative n, this will be useful a lot of times, is equal to z to the negative 1 to the n, right? Algebraically speaking. So that means we're going to have
z over a.
Yep. N equals 0 to infinity of, let's see, we have, write this way first, a to the n, just to illustrate what it looks like, a to the n, z to the negative 1 to the n.
Should we keep our exponents positive or negative?
You should, you're saying, should you move z to the negative n to the denominator?
Like, should we make it...
You should make them whatever they are. You shouldn't make them anything. They are what they are going to be.
No, I mean, like, should we make it a over z?
That's what I meant. Yeah, so that's what I was saying. You meant move z to the denominator.
So it could be z over a to the negative n.
Why? Why'd you do that?
No, I don't know.
You're right. Yes, you could absolutely do that. That is a legal algebraic move. If you're a crazy person. So yeah. So let's say, but just for fun, So that means it's going to combine, right? And we're going to have, let's do what everyone wants to do. A over Z to D. Cool. All right. So what that means, first off, is everybody cool with how we got to this place? This is arguably the hard part. Well, actually, like the next step is the hard part. Okay, so for convergence, remember that we need it to be less than infinity, so the absolute value of a z negative 1 to the n, or that one, to be less than infinity, which means we need to find the closed form solution. Now this part is like high school algebra 2, I think. So what we're looking for is this. We're looking for, let me do a different color. N equals 0 to infinity, A over Z to the N equals that collection of polynomials. All right, that's what we're trying to do. So what you gotta do is you gotta look at it and ask yourself, what is this?
A over R, J omega, yeah.
No. What kind of series is it? No. Well, technically, yes, but more importantly,
Geometric.
what's that?
Geometric series.
Yeah. Edward gets another gold star. I'm going to make Edward stop talking here pretty soon so the other kids can participate. Yes, it's geometric series. Does everyone remember those things? A geometric series, an exponential series, like all the, like I said, high school algebra 2, you learned what these guys equal to? Yeah? You should have.
I didn't learn this till Cal 2.
You learned still Cal 2? Okay, cool. All right. Yeah, so this is what's called a geometric series. So there's books of different types of series. A popular one that's going to appear for our types of applications is this one. It's called a geometric series. Right? And that basically states geometric series by definition is k equals 0 to infinity, a times r to the k is equal to a over 1 minus r. Cool. So what does that mean for us? So if we have n equals 0 to the infinity, a over z to the n, what's our r? Anyone besides Edward?
Is it 1 over Z?
What's up?
1 over Z.
It's not 1 over z. Don't get so the fact that we're using a in this term is a little bit confusing. They're not the same a. Should have used a different thing. The definition I found also included a. It's a over z, right? It's whatever's in the whatever's wrapped up in the exponent. So yeah, so r is equal to a over z, and our a in this term is what? Just 1, right? Anything that was multiplied by that term. Which means that our closed form solution 0 to infinity, a over z to k is equal to, a is 1, so it's going to be 1 over 1 minus a over z, which we will algebraically simplify by factoring out that z to get z, because remember it's got to be polynomials, z minus a. So that's A. A has some value. Now we need to go ahead and plot our guy here. Real. What a guy. Okay. Real, imaginary. And let's see, now what? What happens now? Where do we draw this circle at? Where does our sequence converge? And the answer is here, since as that gentleman let us know, we're almost out of time, so we'll kind of wrap this one up. Is you gotta look at it and say, well, where is it going to be equal to 0, right? If r is equal to 2, what is this going to be?
R is equal to 2?
Yeah, well, if a over z is equal to 2, what is our whole sequence going to go to?
1.
That's 1.
Infinity.
It's going to go to infinity, right? Because it's an exponential thing. Right? It's got to the k. So that means that, I should have wrote this in. But that means that this a over z, or rather the absolute value of a over z, has to be less than or equal to 1, right? Which means that if we do algebra, the absolute value of z over the absolute value of a over the absolute value of z has to be less than or equal to 1, which means that absolute value of a is less than or equal to the absolute value of z. That's the punchline. That is why I can't draw a box. Fine, you win one note. Just 2 by hand. Right? Is our rule for convergence for this sequence. So if we go back now to draw it, is it going to be a disk, a ring, or a hole?
A hole.
Yeah. There we go. Okay. So yeah, so there's going to be the circle with A being right there, and our region of convergence is z greater than A.
So are we gonna have to memorize like all of those series like again, or can we have like?
Technically, yes. However, there are a handful of them that are going to come up a lot, such as geometric series.
So like on tests, will those be given, like those identities?
Well, you're testing the take-home exam, man. So
Oh, okay.
yeah. I mean, if you want to like be hardcore and be like, I'm going to memorize everything. I'm not going to use anything. I'm going to do it. I'm going to do this take-home exam, closed book, closed. No, if you want to be that guy, that's badass. You should do that, but you don't have to. Yes, you can use whatever.
Okay.
Yeah, it's take-home exam. So, all right. Any questions, comments, concerns?
How many holes are in a straw?
How many holes are in a straw?
1?
Infinite holes in a straw.
One hole. Same hole.
So is it an infinite
If you
straw?
dig a hole like 3
Well, in the straw, yeah, I guess you're right. It would be one hole. Yeah.
What do you think, Christian?
Definitely 1.
Yeah, it's definitely one hole.
It's definitely.
Your
All right. Bashir wants to know, Do you know approximately when we'll have our first exam? Friday. No. I don't know. I don't know, when do you want to have it? In a month? Yeah, probably like in a month. I mean, we got to get through chapter 2, because it's basically 2 halves of the course roughly breaks up into 2 halves. There's the part we're in right now, which is where we're like learning the stuff that we need to know in order to do the interesting things. When we finish that, we'll take an exam over that stuff. And then we'll do all the interesting things, and then we'll take an exam over the interesting things. So I will loosely say, yeah, it's just never. And probably in about a month, we'll take the exam. So, cool. All right, that is it for class today. We're still in this like weird esoteric kind of abstract place, so there's no homework assignment today. So enjoy working on your projects. We'll probably give you something to do on Friday over the weekend, but maybe not. So, all right, I'll see you guys on Friday. Thank you. Yeah, Cole's right, Bashir. The geometric series has to converge has to have R's less than 1 or less than equal to 1 to converge for the geometric series. I guess it has to be less than 1. I screwed that up. You're Ratza.
Hey, Professor, my bad. I'll stop.
I'm just teasing you, man. It's all good.